Hello, first year EC students. I hope you have seen the video of dual circuits concepts of the two theorems left in the second unit. Now, this is the video for fourth unit. I said you that third unit is also there, but we will see the third unit later. We will try to complete the fourth unit and fifth unit. This is the fourth unit. In that fourth unit, we have two parts. One is magnetic circuits and the analysis of simple magnetic circuits, and then next part is resonance. So the resonance phenomenon in AC circuits. First part, that is magnetic circuits. In that, self-inductance, mutual inductance and concept of coupled circuits we have to see. Coupled circuits or coupled coils. These self-inductance and mutual inductance are the terms generally referred to coupled coils or coupled circuits. You see here, coupled circuits. Coupled means magnetically coupled. So these are also called coupled coils. Generally, when we will say magnetically coupled, if the flux of one coil links with the other coil also, then we say that these two coils are magnetically coupled. So there is a magnetic coupling between these two coils. That is mentioned here. You see here, the coupled circuits refer to the circuits involving elements with magnetic coupling. Two or more elements that are magnetically coupled are known as coupled circuit. If you place a coil nearby to the another coil that is having some flux, automatically some flux will be linked to the another coil. Then we can say that these two are the magnetically coupled coils. In magnetically coupled elements, the power transfer occurs through magnetic flux. In such a magnetically coupled coils, power transfer from one coil to other coil generally happen through this flux, that is flux as a medium. Whenever current passes through a coil, flux is set up in the coil, that we know. Every current carrying conductor is surrounded by the magnetic flux. So therefore, if a current is flowing through the coil, magnetic flux is automatically set up. If the current through the coil is DC current, then the flux is DC current or constant flux or steady flux. If the current flowing through the coil is alternating current, then the flux is also alternating. I think you also know the Faraday's laws of electromagnetic induction. That Faraday's laws explain about, or Faraday's laws says that whenever there is a change in flux linkage in a coil, an EMF is induced in the coil. That is the Faraday's law. Of course, there is second law also that says that will tell about the rate of, that means magnitude of the induced EMF. But mainly the Faraday's law means if there is a rate of change of flux linkage, an EMF is induced in the coil. By that principle, if a coil is there and if some current, alternating current is flowing in that coil, then we will be having now coil and alternating flux. Alternating flux means changing flux with respect to time. Now coil is there, changing flux is there, then automatically by Faraday's laws of electromagnetic induction, an EMF is induced in that coil. So this EMF is known as self-induced EMF. This EMF is called self-induced EMF. When a circuit has two or more coils, that means coupled coils, just now I said, if there is another coil nearby to this coil, then there is a possibility of the flux produced by one coil links with the other coil. Now what happens if a coil is placed nearby to this coil, as this flux produced by coil 1, that is alternating flux, you remember, that links with the second coil also, then now there is a situation, that is coil is there, second coil, and alternating flux is there. Then automatically what happens by Faraday's law? Some EMF is induced in the second coil also. You see now, because of the placement of the second coil nearby to the first coil, EMF is induced in the coil also. If EMF is induced, then if we can use that EMF by closing a circuit, automatically current flows and power also there in that circuit. Now the power transfer from first coil to the second coil is now, you tell me how power transfer is taken place by means of this magnetic flux. So power transfer or power is transferred from first coil to the second coil through the magnetic flux. That is what I said in the first paragraph, that is where it is power transfer. Power transfer here takes place through magnetic, you see, the magnetically coupled elements. The power transfer occurs through magnetic flux. So that is, hope you have understood. By Faraday's law of electromagnetic induction, a self-induced EMF will be induced in coil 1, and if coil 2 is placed near to this coil 1, some amount of flux of coil 1 links with coil 2 also, and in coil 2 also by Faraday's law of electromagnetic induction, EMF is induced. If EMF is there, we can utilize it for power. So this is about the coupled coils, magnetically coupled or linked coils. The best example of this coupled coil is transformer. You see here, the transformer is the best example for coupled circuit. In transformer is the same thing or same phenomenon is taking place. In transformer generally there will be two coils. One coil is called primary coil, to which we will give the supply, alternating supply. That means alternating current we will give to the first coil. Automatically alternating flux will be produced in the coil, and we place second coil called secondary coil near to this coil. Generally in transformer, these two coils are wounded on a low reluctance core. It is made of iron or some magnetic material. A core is taken, and on that core first coil and second coil is wound. This core is to provide or to establish a low reluctance path. Previously in our previous explanation, I said one coil and another coil placed nearby. There we assumed that these two coils are placed nearby in air. There is no core, just placed near to each other. But in transformer not like that. A core will be there, and on that core first coil is wound and second coil is also wound. As I said, this is to reduce the reluctance. In the air, generally the flux linked with the second coil is somewhat less because of leakage. Our air reluctance is more, so only some portion of the flux will be linked with the second coil. But in transformer, as I said now, there is a core. Because of that, maximum amount of flux produced by coil 1 links with the coil 2. So like that, transformer, in the transformer there will be two coils, primary coil and secondary coil, and this transformer is the example for coupled circuit. For primary coil we will give the supply, flux is produced, this flux links with the secondary coil, and in secondary coil also some EMF is induced. This is EMF. This EMF is called secondary EMF, and we can connect load to the secondary circuit to utilize this electrical power. Now, in the transformer or in the primary, in the coupled coil, you see here, the EMF, the induced EMF in primary coil is called self-induced EMF, self-induced. Why? Because current is given to that coil, and in that coil EMF is induced. That is the reason why we used the word self-induced EMF. And we have seen that some amount of EMF is induced in the secondary coil also. This EMF is called, you see, mutual induced EMF. This is mutual effect. Why? Because here there is no current. This is because of the mutual induction from the other coil. EMF is induced. Both the EMFs are induced based on the Faraday's law, but there is a slight difference. In the first coil, as current is flowing in that coil itself, that is called self EMF. In the second coil, the current and flux is because of the first coil. So EMF is mutual EMF. So these two are the EMFs. So that is about the self-induced EMF and mutual induced EMF in coupled coils or transformer. Next, this is dot convention. This we will see after some time. This is used to follow a sign convention for the two EMFs that we will see next. But first of all, we will try to define self-inductance. Self-inductance. We have already seen inductance. It is measured in henries and it is the property of the magnetic coil. We have seen that inductance is the ratio of flux linkage to the current. Flux linkage to the current. To define self-inductance and also mutual inductance, consider a coil with n turns. With n turns, this is the coil. Let the number of turns in the coil are n. Let the coil is carrying a current I amount of current is carrying alternating current. Let phi be the flux produced by that coil because of the current flowing. Now as this flux is alternating flux, an EMF is induced, as I said just now. That induced EMF, here you are having only one coil, current is flowing in the coil and EMF is induced in the same coil. So therefore this EMF is called self-induced EMF, as I said just now, self-induced EMF. This self-induced EMF is because of the Faraday's law, and that EMF can be expressed like this: E equal to L di by dt. You know this formula, this is a famous formula for known formula for the inductance. E equal to L di by dt. This EMF can also expressed as d psi by dt, that is rate of change of flux linkage. Flux linkage means here n into phi, product of n phi. This is the flux linkage. So if that flux linkage changes, then EMF is induced. This is our self-induced EMF. So the induced EMF can be expressed like this: L di by dt, or also d psi by dt. This d psi by dt is again, you see here, written as n d phi by dt. N is taken out and written n d phi by dt. If you can equate these two, L di by dt, both are the expressions for EMF, L di by dt and n di by dt, and by simplifying we will get L equal to, you see here, L equal to n phi by I. This is the expression already we have given in the definition of inductance in the first unit. So inductance can be defined as ratio of n phi by I, that is ratio of flux linkage to the current. This is all about the inductance. So for this coil, the self inductance of coil L is given as N phi by I, where N is the number of turns of the coil, phi is the flux produced by the coil, and I is the current in the coil. Because of this current, flux is produced. So the ratio of all this coil terms, N is the coil number of turns of this coil, one coil, first coil. Phi is the flux produced in the coil. I is the current in the coil. So ratio of N phi to I is called the inductance, and here it is called self inductance. Why? Because we are having only one coil and all this phenomenon is happening in that same coil. Now we will go to the mutual inductance. The term mutual comes or is generally referred to another coil. You can have an example. Mutual inductance. If there is a student is there, if he is a good student, then another student who is close to this student will also automatically becomes good. If the first student is a bad student, then automatically the friendship of this student with another student results in a bad friendship. That means second student also will become bad. Here the effect is mutual effect of one student on the other, like that. The term mutual generally comes into picture whenever there are two or other coils or persons. So now the mutual inductance is the term generally related to the second coil. To define this, let us consider two coils, coil 1 and coil 2. Coil 1 is there and coil 2 is placed close to that coil. Let us assume, as before, coil 1 is supplied with an alternating current I1. So therefore some amount of flux is produced in that coil, that is phi 1. You see here, I1 is the current to the coil 1 and phi 1 is the flux set up in coil 1, and you see this term, new term, phi 1 2 is the flux produced by coil 1 linking coil 2. As coil 2 is placed close to the coil 1, some amount of flux of coil 1 linked with the coil 2. Let that flux is phi 1 2. Now we have already defined self inductance or self induced EMF. Now as there is flux in the coil 2 also, by Faraday's law EMF is induced in the coil 2 also. This EMF is called mutual induced EMF. You see, the mutual induced EMF in coil 2. This is proportional to the flux. This and all same thing. We need not consider all these things. We can directly go to this definition. This definition, as self inductance is ratio of flux linkage to the unit current. Here also, this is also ratio of flux to the current, flux linkage to the current. You see previously here the flux linkage to the current, like that. Here also mutual inductance, it is also inductance. This is also ratio of flux linkage to the current, but that flux linkage is slightly different. You see here, it is the product of N2, phi 1 2 and I1. So the mutual induced or mutual inductance can be defined as N2 phi 1 2 by I1. N2 means this number of turns of coil 2, and how much amount of these coils, these turns, how much amount of flux is linked to these coils, phi 1 2. We have already explained. Out of some total flux, some total flux of coil 1 some flux is linking with this coil 2 having N2 turns. That flux is 512. So flux linking with the coil 2 is 512. So that flux is to be used. So number of turns in coil 2 and that flux 512. N2 512. And this flux is because of coil 1 current. There is no current in coil 2, coil 1 current, and that is current is I1. So therefore M12 equal to N2 512 by I1. This is also flux linkage to the current, but flux linkage here is N2 512 I1. In a similar manner, we can say that if current is given to coil 2 and coil 1, in coil 1 EMF is induced, and if you want to see this EMF, this is also mutual induced EMF, and that EMF is also due to mutual inductance M21 here. Because of this coil 2, EMF is induced coil 1. So EMF, mutual EMF, and that mutual EMF is due to mutual inductance M21. That M21 now you see here, you can write straight away like this. Based on this definition, you can now directly write mutual inductance of coil 2 to 1, M21. You see here how it is written, N1 521 by I2. Now EMF is induced in coil 1, so therefore N1, and this EMF is due to some amount of flux of coil 2, that is designated as 521. So product of N1 521, and this second coil flux is due to current in second coil, so that is the reason why I2 is coming. So this is mutual induced EMF from 2 to 1. Because of that, EMF is induced in coil 1, like this is. So this is M12. In a similar manner, this is M21. We can assume that if there are no changes in physical conditions of the coils, that means number of turns, the distance between the two coils, etc., as there are no change in these two coils, we can say that M12 equal to M21, and that equal to M. Or you see here 512 equal to 521, both are same. That means flux produced by coil 1 linking coil 2, 512, is equal to flux produced by coil 2 linking coil 1. Both are same if there is no change in physical conditions. Then automatically M12 equal to M21, that equal to M, and it is called mutual inductance. So these two are self-inductance and mutual inductance. Both are inductances, ratio of flux linkage to the current. But self-inductance means it is related to single coil. Ratio of flux linkage of same coil to the current flowing in the same coil, that is self-inductance. Mutual inductance comes into picture when there are two coils placed closely. Because of flux of first coil, EMF is induced in the second coil. That EMF is due to mutual inductance, that is M12. In a similar manner, if you give supply to the second coil and examine the current in the examine the EMF in the first coil, that is M21. It is a reciprocating phenomenon. That is about the self-inductance and mutual inductance. Now, coefficient of coupling. We said that some amount of flux produced by coil 1 linking coil 2. How much amount of flux is linking? If we want to measure this, then there is a measure, there is a quantity called coefficient of coupling. If total flux produced by the coil 1 links with the coil 2, then we can say that 100% of flux produced by coil 1 linked with the coil 2. Then we say that coefficient of coupling is 1 or 100%, fully coupled, strongly coupled. Or if 80% of the flux produced by coil 1 links with the second coil, then we say that Coefficient of coupling is 80% or 0.8. Like that, to have a quantitative measure for how much amount of flux produced, we can do that by using a quantity called coefficient of coupling. To define this coefficient of coupling, let us take two coils. Let phi 1 is the flux produced by coil 1 and phi 2 is the flux produced by coil 2. That means assume that both the coils are supplied by current. Now, as these two are placed closely, some amount of flux of coil 1 links the coil 2. Let that flux is phi 1 2. In a similar manner, phi 2 1 is the flux produced by coil 2 linking coil 1. If these are all the quantities, now coefficient of coupling can be written like this: K equal to, you see, phi 1 2 by phi 1 or phi 2 1 by phi 2. So how much amount of flux produced by coil 1 link the coil 2, that is the ratio. If you want to say, that is coefficient of. Similarly, how much amount of flux produced by coil 2 linking the coil 1, this ratio is called coefficient of coupling. I said just now, when K equal to 1, just now I said total flux is total flux of coil 1 linking with the coil 2, totally linking, 100% coupling, strongly coupled. You see, when phi 1 2 is not equal, this is a very rare case. When non-linear circuits like that we will be getting. If this is the case, then K1 is different from K2, but in majority of the cases we can say that these two are equal. So therefore, K1, this is the case, K equal to root of K1 K2 happens when there is difference in the medium, and like that we need not consider that. We can take as a general rule only K, one value, that is when phi 1 2 equal to phi 2 1 and phi 2 1 equal to phi 1. Now, to get a relationship between L, M and K, we can make use of the previous expressions. We have already explained or defined M12 and M21. M12 is this, M21 is this. Take a product of M12 and M21, this and this. As I said, for majority of the cases, M12 equal to M21, that equal to M, and also phi 1 2 from this relationship, phi 1 2 equal to K phi 1 or phi 2 1 equal to K phi 2. Make use of that relation also. Substitute all these things, M, phi 1 2, phi 2 1 in this product. So what happens? M into M, M square equal to, in this product, in place of phi 1 2, K phi 1 is replaced like that, and in phi 2 1 place K phi 2 is replaced, and if we multiply all these things, you see K square L1 L2. Here what is L1? You see, this term N1 phi 1 by I1, as per our previous definition, this is equal to L1. Previously it is there in the first page, and this is the definition of L2. So these two are written as L1 and L2. So finally M square equal to K square L1 L2. From this, K square equal to M square by L1 L2, and from this K equal to M by square root of L1 L2, or this. So this is the relationship between coefficient of coupling K, mutual inductance M, and self inductances L1 L2. So that is about the coefficient of coupling, self inductance and mutual inductances. In the next class we will see something more about these coupled coils, how to take or how to consider the EMFs in the coils, that and all we will see in the next class. Thank you. control